So before we begin, let's just briefly revise what each step of variable elimination looked like. So initially, for instance, we are eliminating the variable a, and these are the factors that we currently have. And so each step of the variable elimination could basically be divided into two things. So first, you joined over factors which contain that variable. So in this case, we'll join over the factors which contain a. So those are this factor and this factor. So that will be the join of these two. So this, and suppose this join operation, so join this, and suppose this gives us a new factor which I'm calling f star, and that factor has two variables, b and a. So this is the first step in variable elimination, that you take out all the factors containing the variable to be eliminated and then join them. And the second one is you eliminate that particular variable from the factor that you just obtained. So elimination would basically be summation over a f star b comma a, and this gives us the factor after the variable elimination, which I'll call f1b. Now there's another way to write this which is not explicitly divided into two steps, which just sort of combines this together. So if you notice carefully, f star is just a join of these two. So I'll just write this as summation over a pa, sorry, it should be small a here. So summation over a pa p b given a. So this is just another way of writing the variable elimination step, where we are sort of joining the factors which contained a and eliminating a from the result of the join. So this is the notation that we'll follow for the remaining assignment, but you could essentially just think of this as being decomposed into these two separate steps. Now let's move on to the question that we have to solve. So the first part asks us to look at what happens when we eliminate the variable c. So we already eliminated a and got this factor f1b after eliminating a, and now we are going to eliminate c and see what comes up. So what are the factors which contain c? So it's basically all of these factors that contain c, except obviously f1b. So this factor here does not contain c, but all of the others do. So the way we compute the next factor is we join over all these factors and then eliminate the variable c from that. So it would look like something like this. So we'll basically be just multiplying all these factors together and summing over all possible values of c. So c given b, I'm basically just writing down these factors again. So next one is d given c, e given c comma d, and well, okay, two more to go, plus f given c comma e, and the last one being this, g given c comma plus f. So okay, what are the variables that are present in the resulting factor? So the variables that are present in the resulting factor are b, d, e, and this constant plus f and g. So the factor that's generated is of the variables b, d, e, plus f, and g. So again, you could just think of this as first having joined all these factors together and then eliminated the variable c from the joined factor. And this is just another way of mathematically writing and doing it. So we get, so all of these factors that I've underlined, except for f1b, go away, and we get this one big factor, and we get f1b which remains. So after doing this variable elimination, we have only two factors which remain. One is what we got from the previous step, which is f1b, and the other is f2, and the variables in this are b, d, e, and this constant f, and the variable g. So I hope that's clear. So let's move on to the next part. So in this part, we have already eliminated c, and we have just these two factors remaining. And next, the question asks us to eliminate e. So there's just one factor here which contains e. So we don't really have to join, we can just eliminate e from this particular factor. So the new factor that gets generated will have all the variables here except e. So the new factor f3 will be a factor over the variables b, d, the constant f, and g. And this will just be generated by eliminating the variable e from the factor f2. So this is summation over the possible values of e and f2. I'm just writing down the variables here. So essentially there was just one factor which contained the variable e, and actually this should be a small e. And we just eliminated the variable e from that factor to get the resulting factor. And the factors that remain after this step, so this factor here goes away and instead comes f3. So the factors here are f1 and f3, where f1 is a factor of b and this is a factor of b, d, the constant, plus f, and g. And the next part, so again, after the previous step, so overall we have eliminated A, C, and E. And now we are going to eliminate G. And again, just like the previous one, we have just one factor here which contains G. So we don't really need to join over any factors, we can just directly eliminate G from this factor. And so F4 will basically have the variables b, d, and the constant f. And this is again just eliminating the variable g from the factor f3. So summation over the possible values of g and f3. b, d, f, and g. And after this step, this factor goes away and we're left with f1 and f4. So again, I'll just write it like this, f1 and f4, and the variables associated you can just see here. So this is what we get after we have eliminated the variables c. So first we eliminated a, then c, and then g. So given all the variables that you have eliminated, we are left with these two factors, and the query is probability of b comma d given f. And let's see how we get that. So first we can join these two together to get a factor, say f5, which has b, d, plus f, which is, say, obtained by joining f1b and f4, b, d, plus f. And now if we just normalize f5 such that the rows sum to 1, it just boils down to the probability of, so f5, and then we just normalize. So this gives us probability b, d given plus f. So the answer to this part is just join the two remaining factors and then normalize the factor that you get. And that gives you the desired query. The next part asks us to look at all the intermediate factors which were generated and examine the largest of them. So I'm just listing down the factors that we generated in the intermediate steps, and F2 clearly seems to be the largest factor. And now the question is, what is the size of F2, assuming all variables have binary domains? So F2 seems to have 5 terms, and one of which is a constant. And if all of the variables have binary domains, okay, there can be two answers which you might be thinking about. One would be 2 to the power 5, and the other one would be 2 to power 4. So there are 5 terms in f2, so you might think of 2 to power 5. And there are only 4 variables in f2, in the sense that f has a particular value that has been instantiated. So you might think of 2 to power 4. So let's just look at this slightly more closely. So suppose, just forget this question, and suppose you had to look at, say, this particular conditional distribution. So probability of, say, z given some particular y1. So this would just be represented as two tables. So suppose z could take 0 and z equal to 1, and then you would just have a probability here, say 0.4 and 0.6. So this particular number was just this particular factor was just represented by two numbers. So it's basically the number of variables that count and not the number of terms in the factor. So there are only 4 variables in f2, and each of those could possibly take 2 values. The size of f2, or the number of rows in f2, would be 2 to power 4 and not 2 to power 5. So the answer to part C was 2 to power 4 because we had 4 variables in f2. In this part, we are supposed to find a good elimination ordering. By good, I mean that the largest factor that we generate should be pretty small. So essentially, the maximum size factor we generate should be small. So in the last part, we saw that the maximum size factor had 4 variables. So the size of that factor was 16. And in this part, we are trying to see if we can do away with a smaller maximum size factor. And actually, the hint tells you that the largest factor that's generated has just 2 variables. And okay, so what's the query in this case? So the query is p b comma d given plus f. So what are the query variables? So b is a query variable, and similarly d is a query variable. Now notice the variable c. It is connected to b, it is connected to d. We'll never eliminate these two because these are query variables. So whenever we eliminate c, let's say the factor that we generate when eliminating c is, say, fc. So the factor that we get by eliminating c will sort of have all the variables that are connected to c that have not yet been eliminated. So this factor will definitely have b. This factor will definitely have d, because we are not going to eliminate these over the course of the algorithm since they are in the query. And this factor might have e, and this factor might have g. So these are the 4 variables which are neighbors of c, or which share a common factor with c. And when we are eliminating c, the factor that we generate will definitely have b and d, and might have e and might have g. So when will it have e? So when we are eliminating c, if we have not already eliminated e, then this factor will have e. Similarly, when we are eliminating c, if we have not already eliminated g, then this factor will have the variable g. So the trick is to see that this variable is kind of the bottleneck, and if you eliminate e and g before c, then fc is small. So that's basically the only trick that this question, or the only thing that this question asks you to figure out, which is that this variable c is kind of the bottleneck, and this is what would result in the largest factor. And if you eliminate e and g before eliminating this, then the factor that you get by eliminating c would be small. So basically, you'll see that as long as you eliminate e and g before c, things will work out. So just as a possible way of how we do this, let's say first we eliminate the variable, say, g. So we eliminate. Okay, the factors that are present are written down here. So what are the factors that contain g? So one is this, and there would probably, okay, yes, I guess this is the only one. And once we eliminate g, the factor that we generate contains, okay, I'll just call that f1. So this will be a factor of C and F. Next, say we eliminate A. So basically I'm just going through any arbitrary order, but I'll just ensure that C is eliminated after E and G. So, okay, let's say we eliminated A. The factor, so A is involved in these two factors, and the factor that we get after eliminating these two is F2, and the only variable it contains is B. And suppose next we eliminate, say, E. So notice that we said we'll eliminate C after E and G. So I'm first eliminating E and then we'll eliminate G. So what are the factors which contain E? It's just this one. And the, oh sorry, it's also this one. And the factor that you get after eliminating E has, okay, let's call this F3. And the variables involved are C, D, and the constant F. So notice that this does not add to the size of the factor as we saw in the last part, so it's fine if this is there. And finally, we eliminate C. Now, the factors that C is a part of were C given V, sorry, I'll use ticks now, this one, and the underlying factors were sort of already eliminated, so it's this one and this one. So these are the four factors which contain C, and after eliminating C, the resulting factor that we get has variables D. So okay, the factor that we get after eliminating C has variables B, D, and the constant F. So basically this factor here was small, whereas in the previous parts of the question where we were eliminating C initially, this factor after eliminating C was huge. So this is one possible variable elimination order. The trick was just, or the key thing was to eliminate C after you have eliminated E and G. In this question we talk about sampling, and the first part is concerned about rejection sampling. Just to give you a brief recap, what we do in rejection sampling is we first sample nodes which do not have any parents. So in this, say we first sample B, get some value of B, then we sample this A, get some value of A, then we sample C given A and B, then we sample D given C. So what I've told you is sort of prior sampling till now. So this basically sampling nodes in the acyclic order or in the linear order of the graph is basically what you do in prior sampling. So suppose you get a lot of samples this way. Say you get S1 equals, say, A equals plus A, and so on. B equals something. Say you get S2, S3, and you get a lot of samples this way. Say S1000 something. And then in case of rejection sampling, you have some evidence variables. So in our case, the evidence variable is A equals plus A. And then you look at all your samples, and suppose S2 had something which was inconsistent with the evidence. So suppose A was equal to minus A, and so on. Then you reject the sample S2. And similarly, maybe S3 also got rejected, and along the way a lot of samples get rejected and some get selected. So you first sample from the base net without looking at the evidence, and then you just reject the samples which are inconsistent with the evidence. So this then gives you a set of, say, good samples, say S1, S5, S20. These are, say, the samples that remained after filtering things out, and so on. Now, so this was a brief review of rejection sampling. And in this case, the evidence is A equals plus A, and this is what the base net looks like. Now, initially when we sample, when we sample the variable A, the probability of A is given by this table. So you can sample minus A with 0.9 probability and plus A with 0.1 probability. So roughly 90% of the samples will have minus A, and 10% of the samples that you get will have plus A. All these samples will get rejected. So there are no other evidence variables. So the only rejection that happens is because of this variable. So 90% of the samples that we generate without looking at evidence have A assigned as minus A, and on expectation only 10% of them will have A as plus A. So on expectation 90% of the samples will get rejected, since 90% of the samples will have the variable A equals minus A in them. So this question concerns with likelihood weighted sampling, which is sort of an improved version of the rejection sampling that we saw in the last part. And so for instance, in this question, we have two observed variables, which are A, so the variable A is observed, and the variable D is observed. And what we saw in the previous part in rejection sampling was that we were actually sampling the variable A. So when we reached A, we could have sampled either minus A, or we could have sampled plus A, and this was with probability 0.9, this was with probability 0.1, and all these samples were basically, so the ones that corresponded to minus A essentially ended up being useless, and these were the samples that we just kept. And the likelihood weighting sort of tries to refine this, or like get over this problem. So whenever we reach an evidence node, so in this case A is an evidence node, we don't sample from it, we just assign the value which is given by evidence. So initially, say the sampling order was B, A, C, D. So what we do is we start with a likelihood weight estimate of 1, and then we sample from B. So let this wiggle indicate that we sampled some value for this node B from the probability distribution PB. Then instead of sampling from A, we just assign A according to the evidence. So in this case, the evidence is plus A, and we update the weight. That is, we multiply the weight by the likelihood of the evidence. So in this case, the evidence is probability A equals A. So the weight just gets multiplied by this factor whenever we reach an evidence node. Then when we reach node C, this is not an evidence node, so we sample from it. So again, the wiggle. So we sample some value C given B comma A. Then we reach the node D. So this is again an evidence node, and instead of sampling from D, we just assign the value D equal to plus D, which is the evidence thing, and we update the sample likelihood weight by the likelihood of the evidence. So W star, or the factor with which W gets multiplied now, is equal to the probability of the evidence. So it's D equals to plus D given the C that we just sampled. So basically here, whenever we reached an evidence node, we did not sample that node, we just assigned that node and updated the weight value. And this is how we get the weights for all the samples in likelihood weighting. So let's just look at what the weights are in this case. So as you can see, there are only two evidence nodes, and the weights are essentially just going to be products of the likelihoods of those evidences. So in this case, the first weight update comes with P plus A. The second one comes when we get to D, which is P plus D, given the value of C that we just sampled. So this will be this. Similarly, in this case, it will be P plus A into probability of the evidence plus D, given the value of C that we sampled. And similarly here, P plus A dot, this is just the same as the above. So P plus D given minus C, and the values here are, so this weight is 0.05 and these two weights are 0.08. So the same thing, yeah. So just as a brief recap of what likelihood sampling was again, uh, instead of sampling the evidence nodes, we were just assigning the evidence nodes value according to the evidence and updating the likelihood weight as the probability of the evidence given the parents of that node. And this is how we get these weights. Uh, so I hope this is clear. Let's look at the next part, which just uses these weights to answer a query. So, okay, I've just copied down these weights in a much nicer font. And what we have to estimate here is P minus B given plus A, or like given the evidence. So what is the total weight of the samples which are consistent with evidence? So this is the evidence. The total weight of the samples consistent with the evidence is basically this, which is 0.05 plus 0.16, so 0.21. So this is the total weight. And what is the weight of the samples which are consistent with the query? So let me call that as query weight. So that is just this particular sample. Sorry, the query is minus B. So it's this sample and this sample. So the weight of the samples which are consistent with the query is 0.13. So this probability is the likelihood or the likelihood weight of the samples which are consistent with the query, which is 0.13 upon the total weight of the samples, 0.21. So again, 13 by 21. In this part, we are asked to look at two different ways of sampling. One is the likelihood weighting sampling and the other is Gibbs sampling. And we are given two particular queries and we are supposed to find out which sampling method might be more relevant where. So let's first look at this query where we want the probability of C where the evidence node is this particular node. So D is the evidence node. So we have D as plus D and we want to estimate the probability of this variable C. So let's see what happens in the likelihood weighting. So in likelihood weighting, we first sample A from the distribution PA, then we sample B, then we sample C. So C gets sampled after A and B have been sampled. And then when we come at D, we just assign a likelihood weight to that sample. So based on the evidence. So we assign a sample weight, which is probability of plus D given C. So notice that the sample of C that was generated did not depend at all on D because we first sampled A, then B, and then C. So the evidence did not come into play when we were sampling C. It was only when we were weighting that sample that the evidence came into account. So what might go wrong with this? Suppose, okay, let me try to give a very convoluted example. Let's say based on these two variables, A, B, whatever probability distributions they have, and this, say the most possible sample for C was, say we would get plus C with 0.95 probability. So basically when we are sampling, we don't have any evidence till point C. And say we get minus C with probability 0.05. And only then after that, when we look at D, do we take the evidence into account. Now the issue that might happen is maybe plus D is really incompatible with plus C. So for instance, this probability P plus D given C might look like P plus D given plus C is say really small, so like 0.0001, and say the other thing probability plus D given minus C is say reasonable, say it's 0.5 or whatever. But basically most of the samples that we are drawing are with plus C, And then when we look at the evidence, we weight those samples really small. So essentially, most of the samples that we are drawing are weighted with a very, very small weight because the evidence that we take into account later reduces the weight of those samples. And due to this, we might have to draw a lot of samples to have had samples with a reasonable amount of weight, and only then we could sort of estimate the distribution PC given plus D confidently. So the problem that was happening was that when we were sampling this variable C, we were sampling it only based on this part of the Bayes net, and the evidence was, so to say, downstream, and that was then later affecting the weight of the sample, and in bad cases it is possibly giving a very, very small weight to the samples. So in likelihood weighting, it's not very good at dealing with downstream evidence because the samples of the upstream variables might eventually get weighted very small, and you might have to uh, draw a lot of samples to get a good estimate. Whereas for this particular query, the evidence is sort of upstream in the sense you first assign A equals A, or say A equals plus A, whatever, and then you sample C from that distribution. So C gets sampled from like this distribution. So you already assign plus A and then you have a sample of B. So in this case, likelihood sampling is really good because you first assigned A, and then when you sample C, you've already taken this evidence into account. So here you don't run into the problem that you were running into here. So for this particular case where the evidence is already there upstream, and when you sample C, you have sort of already taken into account the evidence when sampling C, or when sampling the query variables in general. In this case, likelihood sampling will do really well because when you sample, you're already taking into account the evidence. So in this case, it's really convenient to use the likelihood sampling. Whereas in this case, this has downstream evidence, and Gibbs sampling is better at dealing with downstream evidence than likelihood weighting sampling. So this particular query we'll solve with likelihood sampling because essentially when you sample C, you have already taken A into account. And this is a case of downstream evidence, and in this case, Gibbs sampling will do a better job of handling downstream evidence since if you remember the Gibbs sampling update, it first assigns something to all variables and then keeps updating a value for each variable. So in the sense, it would have first assigned some value to all the variables, and then when it would update C, it would also be taking into account the evidence downstream. And so basically Gibbs sampling can take into account downstream evidence, and due to that, we'll use this to estimate the other query which has downstream evidence.